Today's lesson is on linearity and symmetry. And what it boils down to today, there are two goals for this lesson. I want you to be able at the end of this lesson and after practicing, I want you to be able to identify whether or not a function is linear. In other words, it represents the graph of a line, or is it nonlinear, which means it's the graph of something other than a line. Can you tell by looking at an equation or by looking at a graph? And then number two, I want you to know whether or not a particular function has line symmetry. Symmetry just means sameness. Is there line symmetry for a particular graph, or is there point symmetry, or maybe a particular graph doesn't have symmetry at all? So we're going to look at this idea of symmetry when it comes to graphs, and if there is symmetry, can we tell whether or not it's line or point symmetry? So to begin with, just real simply, I just want you to be able to identify linear functions when you see them in equation or function form. And we're already used to this, so this should not be anything new. Linear functions can be written in what we would call this slope-intercept form. This is function notation. This is equation notation, but they mean the same thing. F of x and y really stand for the same thing. So let's look at some examples of functions or equations that are linear functions. Like, for example, this first one. You can see it matches up pretty well. M is negative 1/3, B is negative 8. You notice that x has an exponent of 1. The variables in a truly linear function cannot have an exponent other than 1. And so let's try the second one. You might be wondering, well, how does this fit into the linear function example? Well, if you think about it, you could have started off as y equals 0x plus negative 7, and that fits. It just happens to be that m is 0, and we could still think of x as having an exponent of 1 if we want to, but that is the graph of a line. It's a linear function. It's just a horizontal line. So whenever I have y, or f of x, equaling a constant, that represents a linear function. This one's about like the first one. Notice that x has an exponent of 1, which is required. Both y and x have to have exponents of 1 in order to be truly linear, and that's true here as well. X and y both have an exponent of 1. You might be thinking, well, that doesn't look like these. Well, this is called standard form, and the true test is, can it be written like this? Maybe it's not, but can it? And very simply, if we just add 5x to both sides and then divide by 8, and we've done this in the past, we can take what was called standard form and pretty easily convert into slope-intercept form, and now you can see that it does match the requirement of a linear function. So all of these are examples of linear functions. Here are some that are not. Anytime you have a variable in the denominator, that's a clue for you that it cannot be linear. Another way of thinking of this, if you remember your exponent rules, this is like saying 2 times x to the negative 1 power. Well, we already said that your variables x and y have to have an exponent of 1 in order to be a linear function. Well, this obviously isn't 1, it's negative 1. In a similar way, if you notice the second function, x has an exponent of 2. I know this one has an exponent of 1, but this one has an exponent 2, so this is quadratic. So it's not linear. It would be a parabola if we graphed it. And then here we cannot have x and y being multiplied together. That doesn't happen in either one of these forms, the function or the regular equation form for slope-intercept. So that's kind of a giveaway too, that cannot be linear if you see x and y being multiplied together in your equation. Okay, so now that we've seen some examples of what it does look like, what it doesn't look like, on your practice, you're going to be doing that. State whether each function is a linear function, write yes or no, and explain. So let's just run through these real quickly. This first one, I would say yes, because it can be written, it's not right now, but it could be very easily written in that form, f of x equals mx plus b. So that would be my explain. It can be written in y equals mx plus b, or f of x equals mx plus b, which is the form for a linear function. Okay, letter B, I'm going to say no, because the variable x is in the denominator. Variable in the denominator. Cannot happen, cannot be a linear function if that's the case. I'll jump up here to C since I've got these ordered this way. Letter C can't be linear because we have exponent 2, and we said that our exponents for x and y have to be 1, only 1, and that's it. So any exponent other than 1 means it can't be linear. I'll just say exponent has to be 1. This is quadratic. Okay, letter D. Let's see. Well, can it be put in y equals mx plus b? Well, yeah, if we just divide by 3 on both sides, we're going to get y equals 2x plus 3, so we would say yes. And it's written in y equals mx plus b form. And then letter E, another way of showing this, and we'll get into this more later on in the year, but when you're doing the square root of anything, that's another way of saying you're raising that to the 1/2 power. And maybe that's something new that you haven't seen in Algebra 1, but for example, 9 to the 1/2 is the same thing as the square root of 9, which is obviously 3. But the point I'm getting at here is x would have an exponent of 1/2 if we raise everything in the parentheses to the 1/2 power. And we said earlier that x has to have an exponent of 1 to be linear. And so x must have exponent of 1. Okay, and it does not in this case. So I hope you've gotten enough examples of when you can identify linear by looking at a function or an equation, and you'll be doing some of that in your practice in class. All right, and then we're going to look at this idea of symmetry, and I've given you some graphs, and you'll be doing the same thing when you practice. You're going to be looking at graphs, and you're going to decide whether or not a graph has line symmetry or point symmetry. It is possible that it doesn't have either, doesn't have any symmetry. So let's just take a look at each. Line symmetry would mean that I could draw a vertical line, and I would basically have the same, it's almost like you could fold this line on my vertical line, and you would have this a replication or a mirrored image on either side of the fold. Okay, so anywhere, let's just say I drew a line here at x equals 1, and I folded this graph paper on that line, just pretend like that's a crease. Would this side of that vertical line map on top of this one? And I hope you see that the answer would be no. It doesn't have line symmetry, but it does have point symmetry. So let's talk about that. It doesn't really matter where I make a point on this graph. Maybe I'll do it in red, it shows up a little bit better. Let's just say I put a point here, and then let's rotate. You kind of have to use your imagination a little bit, but think about rotating 180 degrees. Okay, so we're going to take this arrow and we're going to move it this direction, and then this one will move in this direction. And basically 180 degrees would mean that this arrow is going to spin and come down to this one, and then obviously this one would do the same thing. Well, do you see that a rotation of 180 degrees basically moves this line so that it's back on top of itself. And anytime you can do that, then you have point symmetry. Okay, so a rotation of 180 degrees, and you basically have the same graph. You have the same line in this case. So this would have point symmetry. And identify any lines or points of symmetry. Well, the thing about a straight line like this is that's going to be true no matter where we are. Any point that I wanted to make. If I were to spin this line around on this point and do the same thing, take this arrow in this direction and this arrow in this one, I'm going to have the exact same line. Now you might be thinking, well, won't this arrow be up this way and this one will be out this way? Well, yeah, that's true, but in essence it's still the same line going forever and ever in both directions. So it really doesn't matter where you are. Any point on this line is a point of symmetry. So we could say it like this: all points on the line are points of symmetry. And that's always going to be true for these lines like this. Okay, all points on the line represent points of symmetry. Okay, well now let's take a look at line symmetry. Again, symmetry means that I can draw line symmetry, in other words, would be I can draw a vertical line, hopefully you can see this, right through what we would call the vertex of this V. And if I folded on this crease, then I'm going to have this mapping right on top of this. This right side would just map right on top of this left side. Okay, so this is an example of line symmetry. Again, just think of the word symmetry literally means sameness. And I will it's like a mirror image that's created by this line going right through the heart of the V. And now we have to identify if it is line symmetry, you need to give me the equation for the line that creates the symmetry, and that would be the line x equals 1. Remember, vertical lines will be x equals, horizontal lines will be y equals. Okay, another example of line symmetry. Notice if I go right through, this would be the vertex of the parabola. And this line that goes right through the vertex creates sameness or symmetry. It's a mirrored image. If I were to fold on in this case, the y-axis, then this right half would just be right on top of the left half. So once again, I've got line symmetry, and I have to identify the line that creates the symmetry. And this would be the line x equals 0, or in other words, the y-axis. Okay, I don't have line symmetry here because if I do draw a vertical line, I don't have sameness on both sides of that line, but I do have point symmetry. And once again, you kind of have to use that idea of a rotation of 180 degrees, or you might want to think too of this idea of a turning point. Okay, can you notice how we're coming up in this direction and then we reach a certain point and then we change. We sometimes in math call this an inflection point. You'll hear that more when you get into calculus. But the bottom line of that is we have symmetry at this point right here called -2, 1. So once again, think of a rotation, rotating this arrow 180 degrees, this one the same way. You can probably see if we spin on this point, then we're just going to be right back where we started. We're going to have the original graph. So we have point symmetry here, so don't forget to identify the point, and it would be the point -2, 1. All right, and so that's basically it. That's what we're going to be after in lesson 2.2, and so make sure you watch this well, take some good notes, and be ready to practice when you come to class tomorrow.